till now. And the second part, I'm gonna give a presentation basically on how AI can be used uh, to recognize human emotions. It will be basically mostly based on images and videos, how we can use them. Um, Regarding the first part, it's just I'm just gonna tell uh, the journey, but this is not something that I'm saying this is a perfect journey or something. It's just something about to guide you what actually I did, and hopefully some bits of it may help you. So to start with, so I got into IIT in 2007. So the rank that I got was not I was not fully satisfied because my interest was more in entering into it. So as you know, the first year is kind of same how courseworks. But at the time, I got kind of high up from learning and confident, but I kind of felt like it's not for me. I went to pursuing that direction, but I didn't have any choice since the selection of. So then the second year was kind of pretty interesting. So then the second year was kind of pretty
stream হোৱা নাই অডিও অহা নাই কি হ'ল
to go for jobs, apply for jobs, and it's just then you apply for universities. So I didn't apply for jobs, so I
নাই
kind of feel
OBS
sure
ইউজ
that
কৰি
I
আছোঁ
want to go join a university, and basically and
কোৱাচোন
then I applied for 4 universities.
খুলিছোঁ
The
OBS
reason
খোলা
that I
আছে
didn't apply for like a lot of US universities is I was actually kind of sure that I wasn't going to join UBC. It was partly because I already had a collaboration through my professor in Japan, which at UBC, University of British
অঁ
Columbia,
আচ্ছা
and
কৰি
then
আছে
I was kind of I got quite familiar with the location, Vancouver, Canada, and also about the labs they have. So, but still, I applied for four, and finally I decided to. So I applied for University of Toronto, RWTH in Germany. It's because there was, I think, kind of a fellowship. I got in, but I didn't join. MIT also applied, but I got a rejection from the labs they have. So, but still I applied for four. But I was pretty happy to get into UBC because it's something that I already decided to. So I applied for University of Toronto, RWTH. So then in Germany, it's I think again this part is important. Like I got in, but I didn't join. MIT also applied, but I joined a university in they have. So, but still I applied for four. So I was happy. That I worked there was pretty interdisciplinary. They were whole different things, all different things. Like I end up adding kind of combining computer vision with so many different things, like biomechanics, neuroscience, eye tracking, face reconstruction, all these different things. And kind of I found that I worked really well in interdisciplinary research. So I still remember that actually when I was working in a project on biomechanics on the facial muscle simulations, like biomechanics, neuroscience. I actually took a course on anatomy case to France, where I did a project on AR that also resulted in a journal. And as you know, if you have a visa to Europe, like countries like France, you can visit everywhere in Europe, mostly Schengen countries. So I also took this opportunity to travel, which I kind of cultivated before. So I visited a lot of countries where I did a project on AR. It also resulted in a journal. And as you know, if you have a visa to 2017 was kind of France, you can visit everywhere, mostly Schengen countries. Kind of I moved to a direction in a way that I kind of finished all my experiments for my decided to and as you know, so 2017 was kind of I moved to visit everywhere, mostly Montreal. Instead of moving from the West Coast, so I kind of finished all my experiments for my. So then I started in December with one of my friends I met there. My current startup, and as you know, and as a part of a startup, it's always important to have the money flow. Kind of raise funding. So in 2018, we raised funding from Dubai. So I was in Dubai for 5 months, staying there. It was pretty nice. Again, another opportunity to travel to a bit around Middle East. But at the time, again, I have to remind myself that okay, I'm doing a PhD, so I have to finish it. So during that time I went back because I knew it was taking too long because I was within my business, but I had to finish it. So I went back to Vancouver during that time and I defended my PhD. It was yeah. So now as such, I think it was kind of also giving me stress at the time because again, as I said, it's pretty hard to do business and PhD at the same time. But luckily, I was just writing my thesis at the time, so I could manage it. So during the time, all these years, I really have learned like all the good, bad, and ugly sides of running a business. Just a lot of sacrifices you have to take. Especially, I found it very hard to balance your personal life and professional life. Of course, everything comes with its with a cost. So, but that's what you have to do. And going out of comfort zone is very hard. And again, so we did a couple of things during this year. We also raised Europe from Belgium. So I was actually also there in Belgium for 5 months, kind of mostly flying on and off from Montreal for every 2 weeks. Again, I did some trips there. And then this year I also moved to Toronto. The difference between Montreal and Toronto is that Montreal is part of Quebec, which is a French Canada, which was I was having a hard time because I didn't know how to speak French. So I moved to Toronto. It's English, so it was better for me. And during this whole year in the startup, we are mostly doing different projects. This year also moved to Toronto. Now working on the difference between Montreal. We have worked in different areas like augmented reality, high dynamic range imaging. So I was having measurements, cloud robotics, and I didn't know how to speak French. And so I use machine learning and AI, but most of the time, if you can do something during this whole year in the startup, we are try to do that, or just this year also we are now working on not a difference between Montreal. We have worked in different areas like augmented reality, I don't work measurements, cloud robotics, learning unless it's really necessary to know how to speak French. And so I use machine learning and AI. So currently I also have during this whole year in the startup, we are on facial emotion, or just my supervisor, and again, my supervisor in Japan internship a long time ago. So we're still in touch. And also doing work with my supervisor, my PhD supervisor startup. I am also helping and consulting on facial emotion. So there I'm working on 3D reconstruction from multiple cameras. And regarding my company, we have still a small team, but hustling, also doing like always. We have 8-person team. We are working on, as I said, on different projects. Currently working on a robotics project. There's always ups and downs, but I love to explore going outside comfort zone and learning new things. And regarding my company, and also currently raising. I didn't really plan it would happen along the way in robotics, but I think there's always ups and downs. One thing I really want to show here is that you never know what helps and learning new things. What company journey helps in what other companies in the future. So it's always important to take seriously make good relations. I visit your supervisors along the way, grab every opportunity you can. One thing I really want to because you never know what else staying at home. You have to explore new things and just try to learn, keep learning all the time. So it's always and try to learn things that can be. I feel like your supervisors along the way, grab every opportunity you can. One thing I really want to learn because you never know what else to be kind of all during this time, especially I feel like to learn, have to keep learning all the time. So it's always try to learn things. Take a lot of different things at the same time. You cannot just always feel like you're learning only this thing. You have to learn all the different every opportunity one thing I really want to learn you should be able to learn that. Research, I think, is something can really help. So this is like a quick journey. So if you have some questions after my talk on AI, you can feel free to ask questions. So now I'll just jump into the presentation. Okay. So so this talk is a kind of introductory, so that even someone who doesn't know about computer vision, they can also follow in. And towards the end, I put some advanced topics, advanced slides, but you don't necessarily have to really understand them. But I hope I'll be able to give an idea of what computer vision and machine learning is, and how maybe in future you can use them in your own projects. And hopefully, and my main goal is to motivate you that why computer vision and AI could be interesting in your career, or just as a project you might be interested in. Okay, so the title says AI knows when you're happy. So human emotion recognition using computer vision and machine learning. So as a human, when you talk to someone, it is pretty easy to find out. I mean, not saying it's very easy, but at least you can guess that someone is happy, sad, angry, but how a computer can know it, it's very difficult, because for human, we can do so many things like so easily, lifting things, moving things, or, because somehow our human body is made in this way, our mind is made in this way that you can process some stuff like evolutionary way very fast or effectively. But for computers, it's very difficult. So now we have to find out that how a computer can find out the emotions just by looking at the image. And one interesting thing is that we know that the human face actually conveys a lot of nonverbal cues, and then subtle cues that actually we can recognize, but we have to teach the computer how to do it. So when you look at a face, there are a lot of things that comes to mind. So if I ask someone that, okay, how can you recognize the emotion? How do you think we do it? So then actually you might say, okay, actually there's some features, on the face that tells me, like, how the eyes are moving, how the eyebrows are moving, the wrinkles, mouth shapes. They all kind of come together and tells us a lot of information, and then somehow our brain processes all these features and then tell, okay, someone's angry or sad or happy. So can we kind of guess? Can we kind of think that we can also do that same thing for computers? Maybe yes. So these are the individual emotions when you look at someone, right? But consider a situation when actually we are also in a kind of a group setting where things get more complicated, because there are a lot of people interacting, and then basically from the face of the people in this particular scenario, it's a painting. It's a famous painting called Unexpected Visitors, where you can see that there's a dynamics going on. Like, someone is happy, someone is sad, someone is curious, and it will be really nice if computer can recognize all these things, in real time, for example, and that can give us a lot of information. So if I zoom into the face, some of the faces here in this painting, you can see the artist has really captured well the emotions. Just by looking at the face, you can say someone is, maybe kind of skeptical, someone is happy, someone is, kind of angry. So as a human, you can tell it, at least to some extent. And we want the computers to also be able to do that. And then if you ask why we need this, so there are a lot of different applications. Human computer, like interaction between human computers is important in many cases these days. Like, you know, a lot of components in this era has been like human components are replaced by kind of robots, for example, and then robots and human has to interact. That's also an example of human computer interaction. In marketing, sometimes they have to know the emotion of the people so that they can provide customized, you know, ads and stuff. Interactive games, maybe like VR games or the games that might involve cameras. They might want to see what your emotion is and customize the games accordingly. 3D animations, and basically it's computer graphics where you are trying to create expressive characters in the games or animations, like movies. So you have to understand about how the emotions are created, how we can capture them from the real characters, and transfer them to maybe animation characters. So those are things, a lot of things you can do it by being able to capture human emotions using computers. So how a computer can do that? So as we discussed before, we talked about how human face has some kind of cues in the face that helps us to find out what is the emotion. Similarly, we can think of from a face image, we can extract maybe some features based on image features. You know, we can detect the eye, eyebrows, mouth, nose, maybe wrinkles. So, and that can, maybe you can use it for emotion detection. So in this talk, I'll focus on face images. There are some challenges, of course. You know, our human eye has this ability to adapt our eyesight according to the illumination. You know, even in dark room, you can see pretty well sometimes, because I mean, in a grayscale, of course, kind of a grayscale, but you can still adapt. But cameras are not always like that, you know. Yes, some cameras now you can see that most of the cameras do this automatic illumination correction, but to some extent they're not as powerful as human eyes. But those are challenges. So like skin color is a big challenge for computer vision, because people from different races have different skin color, and if you train a machine learning model for a particular color, then it may not work on some other colors. So you have to be mindful about what kind of data you're using. You should have balanced data where you use all different colors of faces. Illumination, as I just mentioned, different lighting is difficult, like bright light and darker, or there's no light. So you cannot use some of the algorithms. In fact, like for example, if there's no light, most probably it's better to use an infrared camera where you don't really require light. You can use infrared rays to find out, although you'll not have color, but you'll be able to find the facial features. Occlusion is an issue. Like for example, what if you're wearing a mask? You know, how can you find the expression? Because it might, if you have an algorithm that you trained and using normal faces, and now the input image that they're asking to recognize the emotion has a mask on. So that's a challenge, right? That's one thing. And then movement. Maybe you're moving, and how the computer vision algorithm will adapt to the movement. There'll maybe motion blur, for example. So these are the challenges that we have to take care of. I'm not going to talk about all the challenges, but it's just to remind you that although it sounds straightforward, but there are a lot of subtle things that you have to take care of. It's not that easy. So before we jump into finding emotions, so we have to define what emotion is, like from simple ways, from very simple discrete emotions to continuous emotions. So because we are going to use mathematical models, so we have to also define them and quantify them. So that's important. So the basic emotion that we see was kind of for research was defined in 1972 by Paul Ekman. He just defined 6 emotions: fear, sadness, happiness, surprise, anger, and disgust. But of course, it's very limited. But in many cases, it might just work. So I still remember, I think it was Kinect or something on Microsoft Xbox. They had this basic expression things like they can based on the RGB and depth data, you can tell you one of the 6 emotions. It's pretty basic. You'll work in many cases, but that's not. So the kind of research that I'm working with IIT Guwahati, my collaboration, is to not just stay here, just go through a continuous space where any kind of emotion can be expressed. So that's what our work is. But I'll go there in a few minutes. So in this basic human emotions, some emotions are missing, like contempt. That's one of the drawback. And then it's also difficult to combine the emotions. We don't know. If I combine sad and fear, what will happen? I have no idea. So, and then next, we can go to another model. This is called Plutchik's wheel of emotions. So as you can see in this picture, they have a wide range of a wide spectrum of emotions, although still discrete, but still you can see that now it's covering a lot of emotions out there. So we have 8 primary emotions in this particular case: anger, anticipation, joy, trust, fear, surprise, sadness, and disgust. But I think you can see here in the wheel. And then also there are some kind of new features it was added. They were now you have opposites, like you have joy. You know that joy is opposite to sadness, and which you can figure out in this wheel. And then fear is opposite to anger, anticipation is opposite to surprise, disgust is opposite of trust. So they have defined in a particular way. So for more details, you can go to the original paper maybe, and then you see it. Then they also have combinations, like you can combine anticipation and joy to be optimism, joy and trust to be love. So it's still, as you can see now, it's started giving some more kind of degree of freedoms to go regarding defining the emotion. But again, this still is great. So now there's another model. It's particularly used for continuous defining continuous emotions. It's called circumplex model, where these 2 concepts called valence and arousal. So valence basically tells you it's pleasant or unpleasant, and arousal says whether it's alert or sleepy. And using these 2 bases, you can basically define all other emotions in this 2D space. So here in the x-axis you have valence, and y-axis you have arousal. Then you can see all these different emotions like stressed, excited, serene, relaxed, calm. You can all define all these different emotions. And this also means that since you have a continuous space, you can move from one emotion to another in a way. For example, this curve can move from depressed to stressed to excited to serene. Yeah, it's pretty crazy emotion, but as you can see, you can define all those things. And just to give you an idea, so typically, for example, we can constrain valence from -1 to 1, arousal to -1 to 1, and then you can define, say, for example, if valence is 0.5, arousal is 0.5, most probably it's near this area. So you can say it's a little bit excited, and kind of you can see this combination of excited and elated. So you can define this particular way. You can also discretize the space and define your own expressions related to them. You can tag them accordingly. So now, as you can see, you can define an emotion just using 2 variables into this space, valence and alertness. So just an XY space, in this case VA space, you can define. So what we have learned so far, we had Ekman's 6 basic emotions, which are discrete emotions. Then there's a Plutchik's model, which has 8 basic emotions. They're still discrete emotions, but they introduce opposites and combinations and kind of solve some of the drawback, kind of filled out some of the issues that Ekman has. So they try to address them. And then finally, Russell's model, just to show that emotion is not necessarily discrete. Not necessarily have to define in a discrete way. You can always also define in a continuous way, which will be helpful. And we believe that human emotions are actually far more complex than that, not necessarily just how we tag them, right? Because for humans, we have invented languages, we have defined those terms, anger, happy, sad, but computers doesn't necessarily have to follow those terms. Yes, like we have to be able to interpret it in a particular way from computer's language to our own language, but in general, not necessarily, computer doesn't have to necessarily know is this happy or sad in a very particular way. Like for example, you got a basic idea about this continuous domain, right? Where the computer will only see the numbers, and somehow you'll infer what kind of emotion is, or could be a way to convert those numbers to a particular emotion that we call as, like we know that 0.5 and 0.5 is maybe the excited state, but that example. So this is one of the things that is kind of open problem that people are trying to find. Is there any higher dimension where actually we can define the emotions, not necessarily 2D. Maybe actually we can have maybe like n dimensional, maybe 3, 5, where actually you can traverse in that space and go from one emotion to another, and we will be able to capture more subtle details of the emotions, like maybe combination of 4 emotions, so that we might not be able to exactly tell, but maybe computer will be able to tell, and that's what the goal is, right? And another thing is that can we learn from data, because we have so much data out there? Can we use that data to define those emotions and define the space that computers can use to classify those emotions? So before going to actually recognize, classify the emotions, just quickly see how actually these emotions are created. We knew that we clearly see there's a correlation between emotions and the movement of the face, right? So definitely we have to find out how these movements are happening. It will give us some kind of deeper idea. So of course, when you think about you are surprised, you're maybe raising your eyebrows, right? And when you are maybe excited, you are opening your eyes wide. So how is that happening? So underlying this, there is a mechanism, right? Those are the muscles. So facial muscles generate those facial movements. So when you raise our brows, we actually use our frontalis muscle that is on our forehead, under our forehead skin, and that when it's activated, it basically contracts and then actually pulls those brows up. Similarly, when you blink, there's a muscle called levator superioris that actually, when activated, pulls the eyelid up. That's how you open your eyes. And then there's a muscle called orbicularis oculi. It's a circular sphincter muscle that when it constricts, when it kind of activated, it kind of makes the orifice smaller, and then your eyes close. And it's not as simple as that. The way I'm saying, there are also a lot of other things involved, like a lot of muscles work together. It's not just one muscle. They are interconnected through skin, fat, tendons, and all these other tissues. But when the muscle moves, so because of the constraint attached to the skin, it also moves the skin, and accordingly it produces all these deformations that we make when we have an emotion. And also it's interesting to know that not necessarily we always do it consciously. Also, there are a lot of motions unconsciously, like we don't, when you're happy, you don't think and make this expression of smiling. It just happens automatically. So we kind of learned. And again, a very good example is like your heart is beating. You're not consciously beating there, so there's a muscle there which is doing its work. So in summary, basically there is a tissue system. Mostly it's muscles that when it activates produces the deformation, which in turn deforms the skin because it's connected to the skin, and it produces the facial expressions. So now, what is computer vision? Computer vision is a kind of computer study where we focus on the problem of software. Maybe mute the user. Okay. So computer vision is a field of study that focuses on the problem of helping computers to see. So this code kind of tells it. At an abstract level, the goal of computer vision problem is to use the observed image data to infer something about the world, right? So you're seeing an image. How can you tell something about the scene, about the world, about the environment? And that's what the computers, we expect the computers to do. Related to that, maybe also tell what is computer graphics. This computer graphics and computer vision are kind of opposite way. So computer vision, you look at an image or a video and tells about the environment. But in computer graphics, you create the environment. Like like in movies and games, you see that there's a 3D world, right? So you render those things given some information. So it's the opposite way, just to give a reference. So I think many of you know, but just quickly kind of refresher. So, when you say AI, it can solve so many problems these days, especially recent advancement of deep learning. It's really effective in solving problems, whether it's machine learning, computer vision, natural language processing, reasoning, search and optimization, all these areas. But again, people these days, like AI and deep learning, they just use like as a same thing, but they are not necessarily the same thing, right? So AI is kind of a very bigger sphere. Then there's a subset, which is machine learning is a subset. Deep learning is a subset of machine learning, and then deep learning has so many different algorithms these days coming out. There's so many papers come out every year, and then the ones that we typically heard of, CNNs, RNNs, transformers, is a kind of subset of deep learning as well. But again, that means there are a lot of machine learning algorithms that are not deep learning. So I will highly encourage, if some problem, if you can solve without deep learning, that's okay. I mean, you don't have to show off as okay, I have used deep learning. It's more about the problem that you're solving. If you can solve without deep learning, that's totally fine. But the main part of deep learning is mostly in computer vision, because in computer vision, we have found that from traditional machine learning approach or classical computer vision approaches, deep learning approaches they have performed really well in comparison to them. And that's the reason why we mostly use deep learning in computer vision tasks these days, because they're effective. But we are not like, if something can solve with classical computer vision, that's okay. If we don't need the deep learning. But if we really need kind of a performance in terms of accuracy and stuff, we may want to go for deep learning. But again, remember that deep learning also requires GPUs and stuff. But classical computer vision maybe can get away with the CPUs. So this is something to keep in mind. So now, as we discussed before that, now we want to find the emotion from the faces. So one key thing that you can do is finding landmarks on the face. Landmarks mean there's some image features like your eyes, your eyebrows. So those things actually image processing, using image processing, you can really do it pretty well these days, especially also in deep learning. Deep learning models can really detect pretty well those features. Also, on top of that, you also have some anatomical constraints, like you know that the nose is in between the eyes, it cannot be above the eyes, or the mouth is below nose. So those constraints also help in simplifying the problems and constraining the problem, so that you don't have a big large space to search for when you're detecting those landmarks. So like, for example, in this clip, you can see that the landmarks of the face are being detected. So I'm not sure which model is being used, but there's so many options these days. It's not like back there when I started. We have very, very limited options, and there was no deep learning when I started computer vision. Just classical computer vision using manually basically construct filters, and then you browse. You can basically go around the image and find the features. But these days, manual feature selection is kind of outdated, because deep learning model can automatically do that as a part of the whole deep learning pipeline. So that's pretty cool. So again, human emotion can also be captured using higher dimensional data, like 3D data, because these days you can have 3D scanners that can even these days can scan in real time. And but you have to remember that although we have more data, that means it comes with the burden of more computations, because now they have 3 coordinates, where image has just 2 coordinates, right? And also you need sophisticated systems like scanners and 3D cameras. Of course, there are some cheaper options, but again, for high quality, you might actually not cannot use cheap scanners. Even for movies and stuff, when they do motion capture of face, they actually have a very sophisticated setup, studio setup, where actually they scan them. So it's not something that you can easily get the facilities, and also computation is pretty high. But again, you can capture a lot of details if you have a sophisticated system. But we're not talking about 3D cameras here. So, so there are different ways people have, like researchers, they have tried to define the emotions in terms of some kind of more explainable features. So it's called, one is called a facial action coding system. It's pretty popular in computer vision, computer graphics. Always like pretty simple, but it's pretty effective in many cases. So like, for example, what they do is what is done in this facial action coding system is that they define an expression in terms of some features, some description of the features. Like sadness means drooping upper eyelids, losing focus in eyes, a slight pulling down of lid corners. And anger, they have eyebrows down and together, eyes glare, narrowing of the lips, such as like this way. So, and they define these action units like kinds of modular. You can see that AU1 is inner brow razor, AUT2 is outer brow razor, and so on, and so on. But as you can see that they are kind of, you can see that tells us that maybe they're trying to correlate, they kind of correlates with the muscles, right? Because when you talk about inner brow razor, that means we know that means there's some particular muscles involved as raising the brows. So they kind of translates to the muscles in a way. If you carefully look into it, although they don't specify the muscles, because it's very difficult to define which muscles are responsible for each of them. But somehow it kind of helps us give a correlation between the muscles and the features that we see. So here you can, here I mentioned each unit represents an independent moment that face can produce. And when I say independent moment, of course, they are generated by a set of muscles. And of course, and then other tissues associated with that particular muscle. And then they're related to activation of facial muscles, just like what I said. So here you can see actually, yeah. So even, I think this one is particular is even the muscle name used in 4B. Yes, this thing again I have already explained is a combination of different facial action units. You can define now a facial emotion. So here, like you remember the 6 basic emotions. Now, in terms of facial activities, you can now define it, and all these activities can again map to a set of action units that we saw here, and different action units. Now. Now, one of the very most popular tasks is classification. Right? Classification means just classifying a thing. So, given an image, we have to tell what emotion is that. So, say for example, we have to tell that given an image, you have to tell which of the 6 basic emotions are there, plus one more emotion, which is neutral emotion. We always have that extra emotion. Neutral is because like, no emotion is there. So that's the classification task, right? Classifying an input into some category. In this case, our input is an image, and the category is the classes of emotions. Could be 6 emotions, could be 8 emotions, the way you define it. But also in a dynamic way, if we have a video, how are we going to do it? We also have to track the landmarks. So there's a concept called optical flow that helps us to track those landmarks in different frames. It's very important if you use a machine learning model is to normalize images. So just give you an idea. Optical flow is basically, imagine that there are 3 frames, frame 1, frame 2, and frame 3. You can see the object, this toy example. In this toy example, this object moved, I think 1 by 1 pixel, 2 pixels right. And in frame 3, you can see the frame 2 to frame 3. This object moved 1 pixel right and 1 pixel down. So optical flow will tell you the direction in which pixels at a particular pixel, difference of intensity values, and then doing some more sophisticated stuff, you can tell which direction it moved, and it really helped in keeping track of these landmarks in the face example. Say, and another example of optical flow you can quickly visualize is that say there's a road, it's a video where video of a street, and then cars and this truck is moving forward. And optical flow can tell you in which direction it's moving. And these kind of algorithms are pretty widely used for example, in self-driving cars and those kind of AIs. And these things, this optical flow is even now these days done by machine like deep learning models. When I started, it used to be classical approaches, but even classical approaches works pretty well. But deep learning models accuracy has gone pretty up. And face normalization is just to make everything consistent before you train a model. Because if you train the model with different poses, like say head is tilted, head is forward, then it becomes difficult for the model to train. Difficult for the model to be trained and then predict something consistent. So what we usually do is that, for example, in this particular case, this head is tilted, so we try to align them in a particular way, and then maybe resize it in a particular size so that we have a consistent normalized face. Here, one point you can notice that in deep learning models, usually when you train a model, they expect the image sizes to be same. So if you have one face with, say, 100 pixels wide height, and say it's 100 cross 100 pixels, and one is 200 cross 200 pixels, you cannot give both images as an input. So you have to resize it or reach to same size. So we always do that kind of resizing. It's a part of normalization as well. So as we can just see, normalization and optical flow, this will help us to keep track of the landmarks if we use a video. So if you don't know, machine learning models is basically, if you want to use a machine learning model, there are two steps you have to use. It's training and inference. Training is basically you have this mathematical model, which is machine learning model. So you have, say, a lot of data, which are usually in pairs, your input data and the label of this input data. Then you use all these examples to learn that model. By optimizing the model, you can have a model. And then once you optimize the parameters, you know that this model, say this model need to have A, B, C parameters, these 3 parameters. So by training, you find those parameters. It's like fitting a line to a set of points. And once you train it, then you can use the same model to inference. Like now, since the model has we know the parameters of the model, now we can fix them. Then we can give a new data and give the predictions. These two parts are always there in any kind of machine learning model, any kind of deep learning model. These two are the key steps. Of course, in training, there's some more steps, like where you have to do some cross validations and stuff. So, but I'm not going to go into it. So just to quickly visualize, this is not necessarily you'll do it this way, but to give an idea of how classification can work in a simple setup, like where you want to just estimate the basic emotions from landmarks. So say you have a set of data where you have the facial landmarks and you have the AU values, like what we discussed before, action units. So of course, one of the most tricky part in machine learning is having that good data and a balanced data. And most of the time, you'll find that many times you just have data that was manually labeled. Like for example, someone actually sit there, look at the image, and then say this is AU0, AU1, 2, 5, 6, because this cannot be found by just like in the beginning, first step, you cannot find those. So someone very expert in it, someone he or she will sit and mark them, and many of images, and then use the data to train them all, and then the model can tell what kind of AU it is. But in the beginning, we need some ground truth data, manually labeled data. So that actually takes up a lot of time when someone's working in machine learning to just get the data, good data. Sometimes there are a lot of data out there these days because thanks to people are willing to share them in open source, but many times because maybe you're solving in a particular problem very so specific that you don't have any data. So in that case, you have to create your own. So you can think of classification as okay, so now say you have a machine learning model. Now landmarks could be the inputs, action unit could be output. And you can train this model to predict the action units from the landmarks. Once you have the data, you can train them, and then you can use them for predictions, inference. So another way you could thinking of, maybe you have not only have AU, you also have the emotions, like then actually we can map from the AU to the emotion. So all different ways you can do it based on what your goal is and what your application is and what kind of data you have. So it depends on all these different factors, and then you decide what kind of model you want, what kind of predictions you want to do based on your application. So in this case, you can think of, okay, maybe we can predict the emotions from the action units by using the data that we have. You have seen here, if you use the action units and emotions or AUs, so these are numericals, right? Numerical values. So if they're numerical values, most probably you are okay with using some machine learning models. They're not deep learning models. But if they are images as input, then deep learning, if you use deep learning, then basically you can solve some problems that were not possible to do effectively using classical computer vision. By classical computer vision, I mean where they don't use deep learning. Without deep learning, so you can solve it, but usually, for example, maybe some classical classification problem that where accuracy maybe was like 75 before with classical computer vision, but now with the deep learning you can do it like 90 plus 94, 95. So you can see that big jump is coming because of the power of deep learning models. But what one simple example is, if you have face images and corresponding emotion levels, like say 6 basic emotions for each of them, which one is this? Like say this one is like a fear, something like that. They can directly create a model from face images to that level. So that's pretty cool because now it's become so powerful. You don't even have to define the features. You don't have to do anything. You just need a deep learning model. There's a lot of layers. Always sounds easy, but there are a lot of steps in there because there's a lot of parameters to tune. Like for example, what kind of deep learning model should I use? How many layers of the deep learning model should have? There are a lot of things you have to tune, so it takes a long time. Plus, another challenge is main challenges are you need a lot of data to deep learning to work. Sometimes for classical machine learning, you can get away with classical computer vision. You can get away with maybe 100 data samples, but to train a full deep learning model, you need millions of data. I still remember there's one finding deepfakes from images, from videos. There's a Kaggle competition. Kaggle is this website where people do machine learning projects, but just for fun. And I will show you the link. But there basically is a simple project, but it was using 1 million images just to find the deepfakes to train the deep learning model. So you can see that amount of data you require for the model to work well. I mean, you can use less images, but the performance will not be that well. Maybe it's equal to classical computer vision, but that's not what you're looking for, right? There's some ways to handle this. Even you can, with a small amount of data, you can do it. There's a thing called transfer learning, but again, there's an advanced topic. But I'll quickly go through it in one of the slides in the next few minutes. And second thing is you need to train the model. You need powerful GPUs. In classical computer vision, I never use GPUs. I can always get away with just simple CPUs, but in deep learning, you will need GPUs because that particular example that I told, training 1 million images, if I use CPU, it's going to take me like 2-3 days. But the GPU maybe in half an hour or something, with powerful GPU. But that's even this case. But some of the deep learning models that Google, Amazon, or they're making, they're training, actually even they take like months with multiple powerful GPUs. So it depends what kind of model is. It depends on complexity of the model as well. I was using a very simple model, so that's why I was able to just train in half an hour maybe with GPUs with 1 million images. But there are some models took forever. So you have to be mindful about that. And when you talk about deep learning models, in particular images, so one particular kind of deep learning model works pretty well is they have convolution layers. They call convolutional neural nets, and it's called CNN. They have been pretty successful in kind of doing almost any computer vision task. The power of it comes because, in classical computer vision, you have to manually define the features, like what kind of features you want to see. Like, for example, you can say that if there's a horizontal line, consider it as an eyebrows or something, right? You can define those things manually. But in the power of deep learning is that you don't have to define it. It automatically finds the patterns. Especially this convolutional neural network can apply convolutions on the images and find the local features automatically. And then when you train it, it automatically finds out which of those features are important for this particular task. And as you can see, there are hidden layers. These are all hyperparameters. You have to decide how many layers you have to use. I think some of the things and these numbers you can decide based on your experiments, like based on your experiences, but not necessarily, because sometimes it's very complicated. So you have to maybe train a lot of different models with different layers, numbers, or there's a lot of other hyperparameters as well as a part of convolution. like what is the size of the convolutional kernel, and all those things are there. So you have to do a lot of training, a lot of hit and trial sometimes to find those hyperparameters. But when it works really well. So during the training, basically we want to find out this black box, right? I mean, it's a CNN, but this box we have to figure out, approximate this function. So you can think of it as basically I'm mapping images to the labels, and using this function. And during the training, of course, we cannot find the perfect model, because if we had a perfect model, our result will be always 100% accuracy, but we don't have 100%. So we're approximating this model, and based on how well you can tune the parameters, how well you select the model, how good your data is, you can approximate better and better and better, almost like perfect. So make it better, that means you get more accuracy. So ultimately, once you train it, then basically you can freeze those parameters and just give an input, and it will tell you what is the label, because we already have this approximate model which is known after training, and then generate. So now I'll quickly go through a few advanced models. So as we already talked about classification, you know what classification is. And I also mentioned quickly about the transfer learning, which helps us to do deep learning. Even for us, for newcomers, they can do it deep learning very fast, easily, because the transfer learning exists. Only because of that we can do transfer learning. Otherwise, it will be always confined to companies like Google. But and then I'll briefly talk about embeddings. Embeddings is basically, you can think of the space that I talked about. So like we talked about 6 basic emotions, right? Then we talked about continuous emotions. Now, and the continuous emotion that we talked about was in 2 dimensions. Now imagine there's an n dimension, like say 10 dimension, 12 dimensions. So that space is called embedding, where basically we are mapping the emotions to a space as a point in the space. That n dimensional space is our emotion. So we want to find that point from an image, or where a particular image maps to that point, and then we can tell what the emotion is. So I'm going to briefly go over it. So just quickly about transfer learning. So, you know, when you have defined a deep learning model and then you want to train it with data, so you have to train the whole model, right? So as I said, there's computation time required, a lot of computation time, and hardware is expensive as well. Like, you know, GPU is going to cost you a lot. Even if you use a cloud GPU, it's going to cost you a lot. Maybe it's like every per hour is maybe $1, $2, even for low-end ones, if you use Amazon Cloud. So these are pretty expensive. So what in transfer learning we do is that we don't exactly train the whole model. We actually replace a final layer, final classification layer, or we can only train the parameters of the final layers. So we freeze all the other ones parameters and only use the final layers to train. So what happens is that during the process of training, we only need to learn very few parameters, and this in turn helps us to do it quickly. And in practice, it found that some of the already trained networks, like typically people use ImageNet. It's a big set of images where people classify cats and dogs and all different objects. And then people found that if you take this model and you freeze the parameters until the last layer and then trained only the last layer based on your task, it actually performs pretty well. Like quickly it goes up to maybe 80–90% of accuracy. And in fact, many times it works, that's enough. And you can also tune other stuff that will to further improve the performance. And some of the typical deep learning networks like ResNet, EfficientNet, that can be used for different purposes like this. Internally, they use like concepts like CNN. So just quickly visually to say it, like for example, say this is the input model, the output is the class label, you know, and so here you can see that in this particular model, say these 3 layers at the end are a classification layer for task A, and then what we do is we basically transfer learning is we freeze these layers. We don't update the parameters of this model, these layers, only update the last few. And then we suddenly start seeing that actually the model is being able to do the task B. So for example, maybe this task in the input, so the first model, maybe it was classifying objects, like, you know, it's a house, it's a car, it's a cat, it's a dog. And the same model I used in the second task, where my task is to find emotions, actually we can use it. So that's the beauty of it. And now quickly go through the embeddings that I mentioned about. They have different names. Sometimes they call manifold learning. Like there are also there's different names for this particular thing, you know. But embeddings, they call it different ways. But the whole idea is that how can you map an image to a space, a point in a space where it indicates a continuous motion. This particular Google has this FEC a model which basically use image triplets. It's pretty cool actually. So they basically have three kinds of triplets. One triplet you have all three images from different emotions, and one triplet you have two emotions same and one different, one anything else, something else, and then one triplet with all same emotions. So what they do, then they force one leveler to find the most similar pair. So what happens in this particular case, as you said, they are actually all from different emotions. So how can you select the similar pairs? But they're forced to select two pairs. So that means that will tell us which emotions are closer, similar in nature. And so, for example, say this purple and the blue are, they said similar. They will say that, okay, that means this purple emotion and blue emotions are actually pretty close, but this orange emotion is far. So that information you can get from there. In this particular second case, again, if they select these two, we know that these two are similar and this is different. So we kind of make it strengthen our belief that these two are the same. And in the last one, since they're all the same, if they pick, say this person picks first two, it tells us that even within the same emotions, these two samples are closer, and so this gives us some kind of inter-class distribution, and this gives us more information about the inter-class between different classes, and this is inside one classes how the samples are different. So you know, this way actually you can kind of seeing that how the emotions are distributed in a n-dimensional space. So in this particular case, they basically use a deep learning model, and the goal of this model is basically they take all these three images during training, and then they minimizes the distance between similar pairs and penalizes the dissimilar pairs. So when they do this process, they're automatically generating a space that basically maps those images in a particular way in an n-dimensional space where it becomes easy to classify them. Like for example, if we train this model effectively, this model will tell that, okay, these three images will map to these 3 points. As you can see, these two are similar, so they'll be closer in the space, but this orange is different, so it will be farther away from it. And then once we have this model, maybe it's very easy to classify. For example, say this purple is happy and this orange is sad. So if we have an image, new image, and we map it, and it maps closer to these 2 points, we know that this is actually happy. If it's closer to this, it's sad. So you know, it helps in different ways. So this is the whole why we need a kind of create an n-dimensional manifold using this approach. And finally, before I end the talk, I just want to quickly talk about this model called RingNet. So we've been kind of using it for research as well. So this also includes information of anatomy, like you know how actually the 3D faces during this process. It can give us some kind of more information, and also helps us to create embedding that includes face shape, expression, and the pose, and also creates a generative model. Generative model is basically given expression, we will be able to generate a 3D face with that particular expression. So that will be really interesting. So the whole network actually consists of several of these blocks. This left block is kind of repeated in 4 times, and I'll tell you why. So just let's quickly go through this block. So you have an input image, then it goes through this deep learning model, in this case ResNet 50, and it generates some parameters. And so these parameters, in this case, for example, this red one actually tells you the expression, and this maybe the other ones tells about the shape of the face, you know, those parameters. So it basically image to features, or features that are kind of meaningful. So this red features only talk about expressions. So you can train in this particular way, and then you can map those features to using a model called Flame. Flame is a model that basically can generate 3D model expressions from these particular parameters. And then so basically this model maps from features to 3D. And again, from 3D, you can do a projection to image space to find the location of the landmarks. So it's kind of a, you can see that how useful it could be in this particular example. I will show you. So for example, here you can see that subject A is repeated 3 times and subject B is different. So although subject A has different lighting and maybe even different hair colors, but we know that it's the same person. Okay, so it was manually, we have already labeled it. So we know that face shape shouldn't change, overall shape, general shape. So that could be a constraint. So although the different lighting is the same person, so the face, the bone structure will not change. So in this particular case, say when you use this kind of block, you know that I've already told that these different parameters tell us about expression and shapes. So say there's a set of parameters that tells about the shape, like how the bone structure is. Now, since we know that that parameter should be almost similar for list 3, but not different from this one because it's a different person. So that can be used as a constraint during training. After that, if we go through the whole pipeline, finally, when you project the landmarks on the image, since this is from the same person, if I don't, then some of the bony landmarks will actually map the same point to the image. So and that is also kind of a image level constraint that you can use this training. So when you train this whole model, we don't have to use a ring structure. We can use this block, and you can predict from given an input image, we'll be able to generate these parameters of shape and pose and expressions, and also we'll be able to generate the 3D models. So it could be really interesting because then just given maybe you can imagine that given a video, someone doing an expression, you can transfer that expression to an animation character. So and that can be pretty useful, like say for animation, like movies or other examples. So as you can see, for emotion, like deep learning has so many different aspects, and I hope you got an idea about the usefulness of it and why people are moving towards deep learning based models compared to classical computer vision. But I would always suggest that you always start from classical computer vision because the basics are there. It's very important to understand how classical computer vision works, and then from then you can kind of advance to deep learning. But just jumping into deep learning and blindly using a model will not help you in the long run. So I'll just give an example. So currently I'm working in a project we're basically doing 3D reconstructions from cameras. So some of the basic parts, like how cameras work, how to find a camera matrix that lets you project from 3D space to 2D. So those are classical computer vision. They are not part of deep learning. Deep learning is just a tool to do it, right? So if you don't have that understanding, you'll not be able to do some projects like that. So you really have to understand how camera works, how stereo system works, what are the basic terms that are used in stereo or cameras, what is the classical, how convolution works, how basic feature detection to work in classical computer vision, and then can motivate you to innovate in this kind of models. But if you just look for applications, that's okay, and then you can just quickly pick it and use it. But if you're doing research on it, and I really suggest you start from classical computer vision and then jump into deep learning as you go ahead. My suggestions, the next steps are very simple. If you're new to it, of course, you take a machine learning course and take a computer vision course. So if these two things are very powerful, like you combine them, and I can bet on this, and it's pretty interesting to do computer vision because you can see things like visually. And that's what I really got hooked in, as I said during when I described my career journey. And there are a lot of different resources. I just listed a few, but you can always search. Especially you can go to some kind of machine learning, maybe groups, join some kind of maybe, I don't know, Discord, Slack, and then you ask people out what courses to take, and then of course take your own, so that they just don't take one suggestion and just jump into it. Do your own research, like which one, and listen to a lot of people and see which of the courses that are frequently coming out as a suggestion, and then you can use that. And one of the library that is very useful, I've been used for research, I have used professionally for professional products, production product, as OpenCV. OpenCV is a library that is used very widely in computer vision tasks. So I highly suggest that this is where you start, because my first internship, I used OpenCV and I'm still using it in production. So in last 10, 13, 14 years, it's been always a part of me. So I highly suggest you learn it. And then like for machine learning, I'd suggest you can try Kaggle. Kaggle is a very interesting platform, an online platform where you can solve interesting problems using machine learning, where it gives you an opportunity to try out different deep learning models. And this platform also allows you to join communities where they and you have a leaderboard basically, so you can see how well you are doing. And if you are in the maybe in the first 1 to 3, you can earn a lot of money as well. So if you're the first, so the DeepFake competition I took part in, so I was like, my rank was like 26th or something, but the first rank holder got I think $500,000. So there are a lot of prizes. So good. Sometimes you require those kind of motivations, to go ahead. And also it's a very great community. Even they help a lot, like there are discussions and stuff when competition is going on. People share their work many times. The part that they think that other can be helpful. Some people just go work just for the sake of helping other contestants, not for the sake of winning it. So they share a lot of stuff, and since they are shared by a lot of professionals as well, you will learn a lot how they work, what kind of tricks they use to improve the models, and I think there's a lot of things to learn from there. So I'll just stop there, and I'll be open to questions. So I'll try to answer if you have some kind of queries for both of the parts that I discussed. Thanks. Hello?
Hi, Debanga. I have a question.
Yeah.
Yeah, this is Vijay. So, yeah, I have a question regarding the emotion detection task. So, in any of your work, are you using any kind of multimodal data or models in recognizing these emotions? So, most likely I've seen that this is mostly you are interested in the video or image-based detection, but maybe any kind of speech or text-based detection?
I really haven't used any, because this is kind of a pretty new project that we are doing regarding the emotions, and my whole idea is here in just focusing on finding the embeddings that I talked about. But I haven't really tried to combine different kind of speech or vision, but there's something that we have thought about, but we really haven't worked on that.
Right. Okay.
But there's something really, I think it has a potential. It really has potential.
Thanks for the clarification.
Yeah, no problem.
Hello. Yeah.
Yeah.
Am I audible? Okay.
Yeah.
Okay. So Debanga, thank you for the talk. Okay. So if you have any other question, maybe you can directly ask Debanga.
Yeah. So I think the best way to contact is, I don't have WhatsApp. You can connect me in LinkedIn, and I'll be happy to answer there if you have any questions. Anyone, just maybe I can share my LinkedIn. I have here. You can just search my name, and then you will find me in the LinkedIn.
Okay.
So I'll be happy to answer there if you have any questions.
Okay. Debanga, I have one question.
Mm-hmm.
First thing is that in the first beginning of our video, like our audio was not very good in especially in the YouTube streaming. So I just like to ask one question, can you speak about your startup and what exactly you do in your company?
Okay. So our startup basically there are two parts of it. One part is like we do a lot of projects for our clients. So they have different computer vision, challenges, business problems, and then they ask if we can solve using computer vision. So that's one part we do, and the second part is we are currently also working on a product. It's a robotics product, cloud robotics product. So basically that kind of two sources of revenue. Like one is doing projects, and potentially this product that we are building. and ultimately our goal is to totally transition to the just building products. But currently we are working in both way. So and our kind of projects that we do, as I think I mentioned there during my first part of the talk, we work in AR, we work in high dynamic range imaging, like computational imaging stuff, and currently also working on robotics. And then we have a team for that. So of course I just managing a lot of people in there, but I'm not an expert in everything. But we try to hire the best people, and they can solve the problems.
Okay, thank you. So another question, like this is for our audience only. Like, can you give some idea, like what skills we should have to enter the AI industry? Especially you can speak especially for computer vision or any other data science related task.
Right. So I wouldn't say call myself a data scientist, but I'm more like a computer vision researcher. But for computer vision, basically, deep learning is an essential part of it in many of the tasks, as we know. So some of the things that I kind of used, I can tell you the tools that I have used. Maybe that will kind of guide it. So first of all, for computer vision task, as I said, so that's one. And second thing is you should also have idea about some of the computer graphics tool as well, because it allows you, like for example, say you're doing some 3D reconstructions, which is part of computer vision as well. Some visualization tools, like for example, there's a lot of C++ libraries like PCL, point cloud library. There are a lot of Python based libraries as well. Like one is called Open3D that I'm currently using, that allows you to visualize images and also do a lot of processing of 3D meshes, cleaning up and all the stuff. So that's what we do as well. And I think computer vision, if you talk about from business perspective, it's a bit different. From business perspective, we don't start from technology. We always start from the business problem. So once we know the business problem, then we kind of sit on it, like think about it, how we can solve the problem, what kind of requirements it is. So it's not like straightforward. You can like even for the same problem for two different clients, you might have to use different things, because some client might require real-time applications. Some may say, I don't need real-time, I just now care about the accuracy. And one will say, and the first one might say, I need real-time, but I don't care about the accuracy. So in both cases, it's a totally different problem. Although it looks similar, but so in that case, we might have to select two different kind of models. There are some models we might need to run in mobile devices. So for that, also a different model. So from that purpose, I think that mindset, everyone should build it. Doesn't matter it's computer vision based problems or any kind of other data science problems. You should always start from the problem and design the solution, and then only jump for coding. Just don't blindly use some off-the-shelf model, because that I consider as a hacking. But hacking is always not the most optimized way of doing things. You can maybe solve one or two things as a project, but when actually solving in problems in the real world, it's not going to work. Hacking is not going to really show up in future as a problem. So I would highly suggest you create this kind of a mindset. Start from the problem, then discuss with your team or whoever your mentor, and then discuss how we can design this solution. And then you try different models, and then that's the time comes when you tune different hyperparameters, try different models, and then you solve this problem. And again, you have to come back to design. Maybe you have to come back to design again because you saw that it's not working at all, and that's totally fine. If it's not working, then at least you learn something that is not working. It's not good to like fool yourself that it's working. It's not working again. Come back to the design, the pen and paper, just see why it's not working. So it's a lot of iterations going on, and once you have that, finally you see that all these requirements, this business requirements or the problem requirements it had, have you hit all those things or not? If the requirement says that you need accuracy of 90%, once you reach 90% and you're fitting all this, that's it. You don't have to go for 95. No one has asked you for it. So you have to first clarify the requirements, and then you do iterative kind of modeling, tuning, training, and once you're happy that your particular process is hitting those requirements, then you can say, I am done. So this is the mindset, and for that there are a lot of in terms of tools, as I say, that try to find out the most recent libraries that people are being mostly using. Even like, for example, deep learning, right? So there's so many options. You can use TensorFlow, you can use PyTorch. So I'm not going to say always use, okay, use PyTorch, TensorFlow is not good or something. It's up to you how you find out, right? And also, there are a lot of new libraries coming out with time. So every day, something new is coming out. So be open to that. And, a lot of open sources are coming out. So be open to new libraries, recent advancements, recent papers, and the GitHub, every day new models are coming. Every day, for example, if you talk about image segmentation, segmenting objects from the image, every day, every year, some new projects coming, some state of the art someone is beating the state of the art. So you should keep track of that and then see what it works. So I would highly discourage to just say, I will not say that only use these tools. I'll say just research what is the most state of the art, because this is a field which is like changing very rapidly every day. So I would highly suggest don't stick to one thing. But some libraries, like as I said, OpenCV I have seen, this is like a proven over time. I have seen that I have been using continuously for the last 13 years and everywhere. So this is something that I really highly suggest you learn OpenCV. This is something that personally I really love. Yeah, but the rest of them, there's so many resources out there. I'm pretty sure you can find out what is the current state of the art libraries people are using.
Okay, thank you. Actually, it will be very helpful for everybody. Okay, Debanga, I have another question on the topic. Like you talk about this ring net, right? So actually, yeah. I don't know much about this, but I just want to know about how this disentanglement is handling in that. What about the disentanglement in ring net? Because you are creating different images, like tweaking the one features in that embedding factors. So, like how it is handling entanglement.
So it basically, so as you said, the ring structure. So it basically, after training the models, they didn't specify particularly because it's just paper. It's not something that my work.
Yes,
again,
okay.
Disclaimer.
Okay. Yeah.
But I think I found that once they actually used those constraints, the space kind of came out pretty clean, like in terms of the task they had of generating those expression vectors and stuff. So this model worked pretty well. But again, I would totally say that I would not say some of I also know some kind of edge cases it doesn't work. Like for example, if there are some extreme emotions, like because they internally use this 3D model, right? So and the quality of this construction of this 3D space will be good up to how much this model can is expressive, how expressive the model is. Based on that only you can go how good your space would be. So there I saw some kind of drawbacks of this flame model that I mentioned, this 3D model. Like even if you tune those parameters a lot, like to extremes, so it starts deforming or it's not being able to capture some extreme emotions. So I think that also prevents, so this model is really not good for extreme emotions. When I tested the code, I found.
Oh, thank you.
Yeah.
Thank you. I think we don't have, audience can ask if you have any question directly. I think we don't have any question. So thank you, Debanga. Thank you again.
You're welcome.
Yes. So I think we can wrap up our talk.
Okay, great.
Okay.
Thank you everyone for joining, and then it was really nice.
See you in some future talks again. I'll invite you again for the talk.
Sounds good.
Yeah.
Thank you.
Thank you.
Okay.
Thank you. Thank you, everybody.